topic 3.1, which is on seismic, hydroacoustic, and infrasound technologies and applications. So this topic was already featured yesterday for those of you who attended online to the event with one oral and 3 posters. Today we will have 4 more presentations, oral. And then on Thursday, the session will continue with poster session 3.1. The lightning talks will be in the Wintergarten at 11, and then it will be followed by the poster session at 12 on Thursday. Already at the SNT 2023 and this SNT again, the level of interest is very high, it seems, especially around data quality assurance and control. We have about half of this year's presentations that address calibration and metrology, with seismic applications receiving an increasing attention. I would like also to highlight a dedicated side event on metrology, which will take place tomorrow morning from 9 to 12:30 in the same room. This event will provide a deeper dive into the calibration and traceability issues, which are central to many of the contributions in this topic 3.1. During or after the session, please use the mobile application to vote for your favorite presentations. All these votes will then be accounted for on Friday to award the best presentation prize. So now I think with that being said, we can begin with our first presentation by Samuel Christophersen to speak on infrasound uncertainty propagation, ensuring traceability from the laboratory to the field. Please, Samuel.
Okay, great, thanks. Thanks for the introduction. So I'm going to talk about infrasound. I guess we've lost the slides. I'm going to talk about infrasound calibration, and in particular, the abstract I submitted this is going to be a little bit different than that. So I'm going to be talking about calibration of domes being used for wind noise reduction systems, and comparing that a bit with the results of the rosette-style wind noise reduction systems. So just brief outline, and give a bit of introduction, and talk about how to do on-site calibration, as well as talk about the noise reduction, comparing the dome and the rosette, as well as talking about how the infrasound, the calibration of the domes affects or propagates through to the measure end, so our observations in azimuth and speed. So basically, metrological traceability is the idea that when we have our measurements, typically with a microbarometer, we want to measure pressure in pascals. Usually we end up getting a value in volts or in counts. So what we have to do is then figure out how to convert that to pascals. And so the idea with metrological traceability is that we have these various levels: primary, secondary, field calibration, and finally in situ or on-site calibration of our sensors that allow us to have a traceable calibration back to these SI units, pascals in this case. And I think the thing that I want to focus on as well with this talk is both that on-site in situ calibration, but then also what impact that has on what we're really interested in, because I mean, from a CTBT perspective, we're interested in back azimuth trace velocities, the direction of arrival. And so when we make those measurements of back azimuth trace velocity, what are the effects of the calibration uncertainties on those measurements? And so for wind noise reduction systems, basically they've been put in place to battle basically one of the biggest problems biggest challenges, I should say, for infrasound measurements is wind-generated turbulent noise. And so there are these wind noise reduction systems. For example, in the top picture, we've got this rosette-style one, which is sort of a standard, gold standard, one could say, and is what is installed at, I believe, most of, if not all of the IMS stations. And basically, this averages that sort of turbulence over an area that's larger than sort of the turbulent eddy size, so then we greatly reduce the impact of that noise. Another method that's I think being studied more and used more and more are these domes. So for example, that picture on the bottom is a 2.4 meter metal dome diameter. And the idea of the dome is similar. It kind of breaks the eddies up and averages them out over the surface of the dome. And so then we get that reduction in noise. And so in order to calibrate these on site, we have to bring out a reference sensor, so just a reference microbarometer, and then that's co-located with, for the wind noise reduction, or for the rosette style, we just co-locate it with the Berry center of the wind noise reduction system, and then we can do a calibration by comparison to get a measure of what the response of that wind noise reduction system is, so that rosette, those pipes are. For the domes, one thing that is slightly more complicated. So with the rosette, I had mentioned about it having to be near the Berry center, so that's of the wind noise reduction system. And that's important because if there's a shift in the position of the reference sensor, then that will result in a phase error in the calibration, which would bias our calibration and then bias our ultimate measurements, which obviously we don't want. If we put a reference sensor right next to the sensor under test, so that's that sort of green star there, it'll be under the dome. It's no longer going to be a reference sensor in that case. And so what we had to do is we had to place our reference sensors, basically put 4 of them symmetrically outside the domes to sort of avoid too much of an impact from the domes on the turbulence and on the acoustic signals, so that we'd have sort of clean reference signals, so to speak. And then the idea is for the phase shift, what we do is we basically create a virtual reference. So by taking the average of those 4 reference sensors, that creates a vertical reference that will be centered on the microbarometer, that green star. And that allows us to get the phase shift. And then for the gain, we can't do that because when we average those 4 sensors, that's going to have an impact on the gain of that virtual sensor. So I end up doing a reference to each sensor individually, or a calibration to each reference sensor individually, and then average that to get the gain. And so the next step is to think about how do we make these wave parameter estimations. So for those of you who most of you are probably fairly familiar with this, but I'll just go over quickly the idea. Basically is using the time delay of arrival. So we use this progressive multi-channel correlation, or PMCC, detector and estimator, and it basically uses the arrival times, difference in arrival times at each of the sensors in the array, and then we're able to make an estimate of the azimuth and trace velocity. And because it relies on arrival times, that means it's very susceptible to phase error. So that means that the phase calibration is very important for our wave parameter determination. So quickly here, just show a bit of what is sort of the added or the effect on noise for sort of both these systems. So we have the blue line is showing the ratio of the rosette PSD to a reference sensor power spectral density. And so basically that gives us a sort of an estimate of how much reduction we're getting in noise. This is for an 18-meter diameter rosette with 32 inlets. So this isn't a standard IMS style rosette normally with more like 96 inlets, so the noise reduction isn't quite as good. The yellow line is just so if you notice with the blue line, we have the resonance peak that shows up, but that's not really a peak in the noise, so to speak, because really we're interested in signal to noise ratio, and since that's more of an impact on signal as well, I deconvolved the transfer function, or corrected for the transfer function of the rosette, and that gives us the yellow line. And so we can see that that kind of reduces and then comes back up, sort of approaches to 0 decibels at higher frequency. And then we can see that the orange is showing an example of this is with that 2.4 meter dome that I'd shown in that picture. And so we can see that the frequency range in which they're effective is different, and it depends largely on the size of the rosette or the dome. And so now into some of this calibration. So I did two calibration experiments. One was using a loudspeaker source. So we had a loudspeaker. It was in this sort of wooden baffle that gave a bit sufficient back pressure area for it to generate an infrasound signal down to a few hertz. And it was reasonably pure, especially when we started getting up into higher frequencies around 10, 15 hertz worked pretty well. And we can see we tried this with several different domes, between about 30, 40 centimeters up to about a 1.8 meter diameter dome with different materials. And in all of these cases, up to about 40 hertz, we didn't see any measurable deviations in the gain or in the phase shift. So that's a good, promising result. And the next step was to look at this same dome calibration in the using this Gabrielson method, sort of just in the field. So we had a dome out in the field somewhere in France, and we just let it run the calibration for several weeks to generate enough signal to perform the calibration for, I think it was 8 days worth of data. And we can see here the blue is showing the results relative to the virtual reference, and we can see that, like I say, that gain goes up, but that's in the blue, and it stays flat in the yellow, which is the comparison with the average of each individual reference calibration. But that blue curve going up is because we've artificially decreased or there's basically a transfer function associated with that virtual sensor. So it's not actually the sensor under test or the dome. And we can see that when we do the mean references that we get a flat response. And then what's perhaps, from my perspective, perhaps more interesting is seeing the phase response. So I've never seen any studies looking at the phase response of these domes. And we can see up to about 20 hertz or so, that's phase response stays basically null within the uncertainties that we have. And so that's a good sign. So that means that we're seeing the dome doesn't have an impact on the amplitude or the phase of the acoustic signal. And finally, I want to discuss what are the impacts of that calibration on our observations, so our azimuth and trace velocity estimations. And so what I did here is I took that dome calibration that we did in the field in France and then said, okay, imagine if we had that dome at a station. For example, I used IS-26. If each sensor was that dome set up and had that corresponding uncertainty, what would the uncertainty be in the azimuth and trace velocity? And so we can see I've got, for reference here, we've got the blue curve shows what the calibration or what the uncertainty response is for rosette calibration. The red is a dome. And then additionally, I have the theoretical uncertainties associated with 0 dB, 10 dB, and 20 dB in yellow, purple, and green. And what I guess important takeaway here is that we can see one is that when we look at the dome and the rosette, we're seeing similar calibration or similar uncertainties related to the calibration. So that's a good sign that we're not degrading our results substantially by using a dome versus a rosette. And then the other thing is both the rosette and the dome fall within sort of between an equivalent of between 10 and 20 decibels signal to noise ratio. And I mean, a 10 to 20 decibel signal is a pretty high signal to noise. So basically we're still in that region where SNR is going to be the big battle, and the calibration is not going to be our a main contributor to uncertainty. And so basically, just to wrap up, we saw that with the 2.4 meter metal dome, we saw negligible phase shift up to about 20 hertz or so within the entire IMS band of interest. The uncertainties were similar to that of an 18-meter rosette, as well as being between 10 and 20, between the equivalent of 10 and 20 decibels of SNR. And it would be interesting to do further calibrations of different dome sizes and styles to see if this remains consistent, particularly if you start increasing the dome, will that have an effect on the higher frequency bands? And I guess I'll just, Benoit already mentioned it, but I'll just give a little plug again for the metrology side event that we're having tomorrow morning at 9 o'clock in here. So thank you for your attention, and I'll take any questions.
Okay, do we have any questions for Samuel?
All completely clear? Okay.
All clear? So I'd just like to ask you, Samuel, these domes have been kind of proposed for some time. They've been an alternative to rosettes. How far do you think they are along its development cycle where they could actually be used routinely? You say there's more work to look into.
Well, I mean, in terms of them being used, I think that there's a lot of like more regional stations or national stations that are starting to use those. In terms of calibration, I haven't seen any real like complete calibration analysis like this. So I think that that's something that would be useful to do for some of these different domes, particularly, like I said, if you start having, like for a 2.4 meter dome, that's pretty small, so we might expect that, okay, there's an effect, but it's just too far up in frequency and we don't see it. But if you had maybe a 10 or 15 meter dome, I don't know if people are using quite that large, but I think up to 8 meters has been used, and maybe that would have an impact, start having an impact on the infrasounds region. But that would be further studies that would be interesting to do.
Okay, thank you. Any other questions? We've got time for one more. Yeah.
Out of curiosity, what do you believe would happen to the uncertainty propagation if you change to 3 transducers instead of 4?
If you use 3 references?
Yeah.
Well, I guess it would be, if you set the references up sort of like in a triangle so that it's centered at the microbarometer, I think it would probably, I mean, I think you could probably do it with 2 as well, as long as you had it set up. The advantage of 3 would be there would be a little bit more isotropic. That would probably be more efficient in terms of it would require less sensors. I don't know exactly whether that would have a huge impact on the calibration results. It might, you'd have 1 less sensor, so it might sort of increase the uncertainties a little bit, but I think it would be not a huge difference.
Thank you.
Okay, thank you very much, Samuel.
Thank you.
Thank you, Samuel. Now for the second presentation, we'll have a presentation by Richard Baham on a strategy for the development of metrology to enhance the sustainment of the seismic and infrasound components of the IMS network. Please, Richard.
Okay, good afternoon, everybody. So yes, I'm going to talk about some of the metrology developments that are intended to enhance the sustainment of the seismoacoustic components of the IMS network. Are we aligned? I'm just syncing my... Excuse me a moment, we've gone too fast. There we are. So, all of this fits within the quality assurance work, actually. So quality assurance has been developed alongside the establishment of the IMS network over some years. And you can see here on the right of the screen some of the quality assurance goals that we've set for operating the IMS network. So in fact, if we can achieve the top one of those goals, which is our kind of ultimate objective, then we're in a position where we're strengthening technically the capability and scientifically the capability through having transparency, with taking on board benchmarking, recognition of best practices and so on, and even engaging in peer review processes. So all of these QA activities really strengthen the value of the IMS data. And the range of initiatives that we're looking at are so diverse, and the number of stakeholders and stakeholder groups that we need to engage with is also quite diverse. So I'm guessing that most of you in the audience can identify with at least one of the stakeholder groups shown here. So for these reasons, it's very important to have a strategy for these quality assurance activities, so that we can coordinate the tasks effectively, we can give visibility to what's being undertaken, and we can prioritize. So really the strategy is more of a working plan that can be followed to develop these various initiatives. These strategies take the form of roadmaps. So you can see here the kind of the incarnation of the roadmaps at various stages. So we've got high-level objectives, we've got detailed activity plans, and then text documents supporting the real detail of what those plans involve. So we're developing these roadmaps for both infrasound and for seismic technologies. And really the idea is not just technological advancement, but many of the aspects are also targeting streamlining of activities across the IMS, looking at operational efficiencies, and all of these kind of things are in line with the new sustainment strategy for the IMS to basically streamline and improve efficiency. And we've recognised now that state-of-the-art metrology has a key role to play in these sustainment goals. It's, in many cases, which we'll see, metrology is driving these technical developments that we want to put in place. And the rest of my presentation really is just looking at some examples from the strategy. It's not the complete strategy presentation, but these are some of the priorities and highlights from that strategy. And the first one is field calibration of sensors. And this is something that spans all technologies. But here on the slide, we're looking particularly at seismometer systems. And the needs here are that we need to have traceability, measurement traceability, so it links with the SI. We need to have low enough measurement uncertainties so that any changes can be resolved and not hidden by the uncertainty of the calibration methods. The methods need to be straightforward. We can't really have complicated measurements implemented in the field. And ideally they should have minimal or zero impact on normal operations. We don't want to interrupt the key monitoring activity simply to make routine calibrations. So the idea of them is that they can identify system faults and trends in behaviour and so on. And of course the whole thing needs to be economically viable. So some of the actions we've got here on the plan is to look at current activities, what's currently done within the IMS and parent networks, and then have a steering and monitoring role to look at the research on potential alternative methods, and have a proper critique of those methods, existing methods and potential new methods. We can look at the benefits and limitations of those, and then what we really need to do is formulate new R&D goals to properly evaluate potential new methods. The second aspect I've focused on here is of measurement traceability. Samuel nicely described the need for measurement traceability and what benefits it brings. And here the need is to have a good dialogue with the National Measurement Institutes that are responsible for effectively maintaining the top-level primary standards. The needs also for pilot studies and comparisons, which is a good way of collaboratively developing the technology, but also benchmarking your capabilities at certain points in time. And we need procedures for transferring measurement traceability from the laboratory to the field with travelling sensors, for example. So the activities here is to maintain a liaison with the BIPM Consultative Committee, This is the kind of top-level forum for metrology in this field of acoustics and vibration and hydroacoustics. And this has been very fruitful in the past. With them, we need to formulate mutually beneficial pilot studies and comparisons to validate measurement capability of the key performance parameters for sensor systems that we're talking about. And where possible, we need to look at whether IMS calibration methods are consistent with protocols defined in international standards. So this is another layer for transparency and accountability of methods. Okay, so the final experimental type thing I want to talk about is that of installing seismometers and setting up the orientation correctly. This needs to be rapid, but at the same time technically rigorous. And at the moment, this is quite a time-consuming aspect of station establishment. What's really necessary here is an autonomous method that can be implemented under PTS full control. Right now it requires a dialogue with manufacturers at the time of installation, and given that there may be different time zones at play, this can actually be quite a cumbersome, time-consuming process. So what's really needed here is a systematic, streamlined process with the necessary input from metrology to get that alignment done correctly at the time of installation. So again, we're looking at a streamlining of practice. So the actions here are pretty much like before. Look at what's currently done, conduct some research on optimum methods, and look at the metrology input necessary to get proper validation of the alignment with all the necessary traceability and so on, and then develop software tools that make this a more streamlined job in practice. Okay, so those were some practical aspects. Excuse me. The other aspect of the roadmap is the whole idea of communication with the stakeholders. As we saw at the beginning, there are several stakeholder groups, and each of those need a slightly different approach to the way PTS communicate with those and engage with them. So for service providers, for example, what we'd really like to do is drive research on measurement capability and characterizing sensors, particularly with regard to the long-term or life cycle expectations for sensors deployed in the field. So this is really looking at their susceptibility to the environment and so on, trying to predict what the lifetime of a sensor may be and trying to estimate whether the sensor can fulfill the life cycle expectations that's growing actually through the sustainment program. And then with manufacturers, I think it's very important here to communicate clearly the quality assurance initiative to make sure that it's fully understood, with the requirements are understood, but they're also consistent with what the manufacturer might expect to be in place when they engage with PTS. Obviously, we can't make it extremely onerous that actually it becomes too difficult for the manufacturers to comply with, but at the same time, PTS have certain requirements on them that the supply of sensors and systems needs to be done within a quality regime. And then finally, by talking to manufacturers, we've got a way of keeping abreast with the latest developments, seeing what's coming online, what might be the sensors of the future. And what we really need to do here is agree on a way of having those discussions, whether that can be done in an open forum or whether it needs to be on a one-to-one basis. But whatever it is, we need to do it on a fairly regular basis to agree what the next steps are and stay in touch with these different stakeholder groups. It's also a way of disseminating the strategy and keeping the strategy up to date. And then once we've achieved some things, we can actually communicate those achievements back through case studies and so on to look at the benefits of the QA initiatives on the various activities, whether that's installing sensors or type approving or actually procuring sensors. Okay, and then the next layer of dialogue is with the network and station operators. So here it's necessary to understand what current QA activities are in place, what calibration practices look like, and understand the underlying rationale for whatever those practices are. And then at the same time, we can disseminate the PTS technical requirements for sensor systems and for data integrity, understanding that the PTS role is more of a forensic role rather than a simple monitoring role, which brings certain QA requirements with it. And then hopefully we can find some kind of common ground where the benefits of QA are nicely understood, best practices can be disseminated, and try and get some consistency across different parts of the network in what's actually done in practice. So again, this is a kind of review and respond type activity. So look at how, for example, field calibration is done in different places, come up with a critique of those methods, look at the limitations and the advantages of different approaches, and then put all of that together to look at new ways of doing field calibration, taking the best of existing practices and maybe doing some research on new methods and so on. And also using data coming from the measurement systems to try and analyse how well that system is performing in situ, whether there are any signs of early onset of trends or changes in response and so on. So really getting into the troubleshooting and failure analysis mode to try and keep the sensors operating, but also understand when and why failure occurs. Okay, so last but not least, it sounds, the documentation side of all of this sounds a very dry topic, but actually when you get into it, it reveals lots and lots of interesting aspects, particularly when you start discussing it with the stakeholders and having a review process. You really learn a lot from trying to write down what you do in practice. But the point of documenting everything is to try and give some level of continuity to practices so that the best practices are written down and preserved for future generations to pick up and use or to modify for the better. So actually it's just a way of marking best practices, what's currently done, and having clarity on how the requirements of the operational manual are implemented in real life. So we're working through a whole series of documents to try and capture best practices. It seems like a never-ending task. It's a completely iterative process. As we make one draft, there are some new inputs to capture. So it's interesting in that sense that it's very engaging and very interactive. But we're also expanding the range of documents now to cover things like validation of stations or revalidation of stations, trying to capture equipment life cycle performance and so on. So the range of documents as well as the depth of the documents are expanding. And all of this takes us towards that goal of having continued practice and not losing best practices by staff leaving the system, leaving the organisations and so on. We want to try and capture it all for future use. Okay, so I should say that these roadmaps are designed to be living documents. They're not something we're going to write and put aside for 3 years and try and follow it. The idea is to review them regularly with stakeholders and to take account of progress, technical progress made, changing landscape for these activities, changing priorities, and trying to integrate emerging external developments as well. So we expect to review the roadmaps at least annually to keep them up to date. And this will be supported by a technology horizon scanning activity where we try and keep track of latest developments in the different fields. And we'll do this through participating in conferences like this one, systematic review of scientific literature to capture what's coming along, and market surveys for developments in instrumentation. Okay, so just finally, these technology roadmaps have been invaluable already in directing research and development during the establishment phase of the IMS, particularly with regard to infrasound technology. They represent a clear and preemptive strategy for seismoacoustic technology that remains really essential for delivering the wider IMS ambitions as we enter the era of sustainment. So thank you.
Thank you very much, Richard. We have time for a couple of questions from the audience. Yes, Thomas. There is. Yeah.
You talked about standardization and the international scope. Are there already standardization initiatives in infrasound underway currently? Do you know of some?
Yes, for the international standards. Well, we already have a standard for low-frequency calibration of sensors. This was something we put in place during the last infra AEV project that you were involved with. So yes, we've documented calibration methods for infrasound using piston phone devices, for example.
Is that applicable
Not so much, no. This is really starting the change. This is a way of deriving primary standards from first principles. I guess we could look at then methods of transferring calibration to the field as another method, but that's more of a method standard rather than a calibration specification standard. But that certainly wouldn't be off the agenda. We could look at how that might work.
Maybe you have one more.
Thanks. Yeah, hi, Birger Steen from Northstar. I was wondering, in the sort of larger tech community, there's a practice of users, customers, sort of banding together in user forums and user groups, and that's a quite efficient way to gather stakeholder interests in having a conversation with vendors. Is that something you've considered in this context?
It is, yes. So one of the stakeholder groups was the general user and scientific community. And we did think hard about how to engage with those. And we are thinking about some kind of web-based forum, discussion forum, or actually whether we can piggyback on something that exists already. Just start some new threads up in existing forums could be another way to go. But yes, we're certainly thinking of that. Apologise for my hand, I've got a bright light shining in my eyes.
Thank you.
Thanks.
Any other question? Okay, thank you, Richard.
Thank you.
So for the next presentation, we have Dominique Rodriguez, who will be presenting on exploring the potential of a barometer as a transfer standard for infrasound calibration.
Okay, thank you very much for the introduction. So, yeah, I'm Dominique Rodriguez from the LNI, the National Metrology Institute in France. And so today I propose you to present you a study which consists on exploring the potential of a barometer as a transfer standard for infrasound. For infrasound calibration. Sorry. Okay, so our motivation for this work arises, of course, from in the context of the quality assurance for EMS measurement systems. As you know, the EMS is a key tool to enforce the nuclear test ban treaty, and so ensuring data quality is essential, as supported by the operational manual, of course, but also by the quality assurance infrastructure as presented just before by Richard. And so, in this context, ensuring the data quality requires accurate and, of course, regularly calibrated instruments. So, the infrasound measurements within the EMS must be traceable to the international system of units, and the metrological traceability, this metrological traceability means different needs at different levels. On the top, we will find the first realization of the unit, the primary reference standard, which is usually established by a national metrology institute. And at lower levels, we will find the accredited labs and expert labs, which require working or traveling standards in order to perform secondary calibration of sensors, usually by comparison against such a working standard. So you have here two examples at Sandia and CEA, but sometimes also on field we need such a standard. You have also in the photo another device developed by CEA, which is a portable calibration system, which requires also such traveling standard to perform this calibration. So this study fits directly into that need to find a reliable working or transfer standard for this purpose. So what resource do we have for this purpose? So traditionally, in acoustics, microphones serve as a transfer standard. They are robust and easy to deploy, but more importantly, they are very well established. We have many ways to calibrate them, many standards also, and of course, they are traceable to primary standards. But The only issue is that probably at lower frequencies, in ultra-low frequencies, their performance are lower because the sensitivities dropped, reaching to quality measurement, poorer quality measurements. We have microbarometers. They cover the full frequency range of interest in infrasound, but they are heavy and bulky, and sometimes it's less practical to implement them in the laboratory. And the barometers also, they are robust also, but the main specification for which we are interested here is that they have the capability to bridge the static and the dynamic domain. So this is why I propose to evaluate now. Okay, so the basic idea is to explore how a barometer with its ability to bridge the static and the dynamic calibration domain can be used as a dual calibration device to establish such a reliable transfer standard. So here we tested a barometer, a Keller PEA33X, which it uses piezoresistive technology. In the following operating range. One interesting option of this sensor is that we have the possibility to scale, to range its analog interface to a smaller range to fit better to the infrasound operating range. So here, finally, the objective of this operation is to increase the nominal sensitivity, minus 60 dB here, but to be perfectly clear, these do not change anything on the sensitivity part of the transducer. So it's only a gain on the analog interface. So the advantage is somewhat relative, but in any case, it's better. The second point for why we choose this sensor, and probably it's the most important specification for us, is that it is expected to have a flat frequency response up to approximately 20 Hertz, and this is very important for this kind of comparison because this makes the static and dynamic results directly comparable. Okay, so a few words about the calibration method. So we used two calibration methods. The static calibration was performed by my colleagues from the LNE, the Static Pressure Lab in Paris. They used a method by comparison against a reference barometer and by using also a buffer volume to stabilize the steps of static pressures. For the dynamic calibration, I used, they were provided in my laboratory, Acoustic and Vibration Lab, by using a laser piston phone, a device that we developed specially for calibration of infrasound sensors, in part during the Infra-UV project. So one key point also here is that to provide an accurate comparison basis, we asked to the Static Pressure Lab to calibrate the barometer in a similar range, linear range, that the one used in infrasound. So typically only 10 or 20 Pascal. So we ask them to calibrate the sensor at plus minus 20 Pascal around the atmospheric pressure, which is approximately 1,000 hectopascal close to Paris. Okay, so here, now, this is not the figure. I apologize. I have normally another figure, so well, I will comment. The calibration, static calibration. So here are normally the result for the static pressure calibration. So the calibration cycle was performed with 2 Pascal steps, starting from the 1,000 hectopascal, after increasing of 20 Pascal, decreasing of 40 Pascals, and come back to the initial static pressure. So this simulates like a sinusoidal pattern, but of course here in DC. So this calibration leads to a sensitivity, which the linear regression leads to a sensitivity of minus 60.034 dB with an expected uncertainty of 0.056 dB in this case. So normally you have the output voltage as function of the input pressure, but This figure here is a measurement bias, which is a deviation between the measurement pressure after calibration from the reference pressure. So what's interesting here is that when following the calibration path, we can see like an hysteresis effect, but to be completely honest, at this stage of the study, it was not possible to conclude definitively if it's an effect of the sensor itself or from the calibration procedure. So the question stays open. Okay, here's the result for the dynamic method. So we used the laser piston phone. It was calibrated in the frequency range of 10 millihertz, 20 hertz. So you have the results here in amplitude and in phase. So as expected, the frequency response is relatively flat, with an average value for the sensitivity close to minus 60.04 dB, and the phase tends toward to 0 at low frequencies also as expected. And you can see here the typical uncertainties that we can reach with such a method. The larger uncertainties are achieved at the lower frequencies typically. Okay, so this slide is for the comparison between the static and dynamic results. So as a reminder here, you have the result for the static and dynamic with the uncertainties. So here the sensitivities are seems to in a good agreement within the uncertainties, but to check this more formally, we look for the normalized error. The normalized error is a classical performance criteria used to conclude on the consistency on bilateral comparisons. So the satisfactory range being that the normalized error must be below the unity to conclude to the consistency between the results. So you have here the normalized error as function of the frequency, and as you can see, all the values respect this the normalized error are below the unity, so that we can conclude on the consistency between the result of the static and the dynamic method. Just before to conclude, I just would like to discuss here probably an extra information regarding a potential limit on the static calibration. The fact is that calibrating a barometer with 2 Pascal steps over a 40 Pascal amplitude is very challenging. And this is not a classical usual calibration service provided by the static pressure labs. The usual approach is instead to calibrate the barometer over its full range. This is why we obtain when we buy a new barometer, or if you ask for a usual calibration service, you will obtain this kind of results. So we did it here also. We asked to the static pressure lab to calibrate the same barometer but in the full range with a classical approach. So you can see here the black points reaching to a sensitivity of minus 59.998 dB, so slightly different than the one obtained previously, here the red data. So anyway, there is a small bias. It is covered by the uncertainty, so it is consistent, no problem, but just I would like to highlight here one fact is there is anyway a risk, specifically when the barometer is not perfectly linear, to have a bias or to underestimate the uncertainty with such approach, because finally, so some information is missing when provided such a classical calibration. Okay, it's time to conclude. So the key requirement for this study was to define a transfer standard covering the full infrasound range from the DC. As I said in the introductions, microphones play this role very well for high frequency, typically above 0.1 hertz. And here the barometers can be seen as a promising candidate because the main advantage is we can use 2 calibration paths to calibrate them. So the static method provides very accurate results near to DC and ultra low frequencies, and the dynamic calibration method becomes essential at higher frequencies when the response may deviate from the flat response, and it provides also the phase information, so this is important too. So finally, I believe that by combining these two complementary methods, probably with a smart combination, we could produce a more robust calibration and more robust working standard. For the next step, to be completely honest, my first intention was to present here other results for typically a CETRA barometer, because it is a barometer which is very used also in the community, but I missed some time, so I apologize for that. But it could be a next step to extend this study to other barometers to strengthen consistency and robustness of this study. Thank you for your attention.
Thank you, Dominique. But are there any questions for Dominique from the audience? Darling, you have one. It's coming. Yeah.
Thank you for very interesting details on using the barometer. I think that certainly working proceeding.
It's not working.
This is better. Thank you for a very interesting talk, and I think it seems that the barometers have potential for something. However, I also have one, maybe it's a question. It looks like hysteresis on your going through the plus minus 20 Pascal. It looks like it didn't end the same place where you started. So that's my question, but I also have a few comments. That is 800 kilopascal, 880 kilopascal is not low enough. If you look at all the altitudes you can reach in the world, if you go around in mountains and things like that. So you need to know the dependence of altitude in the calibrations. And also I will say that we are working with microphones a lot, and they can go down to 10 millihertz. And I can say that I have an e-post on Thursday on that. Thanks.
Thank you, Erling. Any other questions for Dominique? I've got one comment. Very early in my career, I was asked whether we could prove that the static pressure Pascal was the same as the acoustic Pascal. And it seems like that's bothered me for a long time. We've not been able to demonstrate that until now, it seems. So do you think that's what you've shown through your measurements, that the static pressure Pascal and the acoustic Pascal are equivalent? Have you demonstrated that now?
I'm not sure I understood the question. Yeah,
So we have static pressure and sound pressure.
Yeah.
Both are measured in pascals. Have you now demonstrated that the Pascal is the same for sound and for static?
I apologize, but the time was too short to present all the details. I specifically removed one slide to demonstrate that it was the same measurement.
Okay.
So, yeah, I can demonstrate it, but I remove it because it was the time was too short to present it. So
that's great. I might.
But we can demonstrate, of course. Yeah.
Thank you.
I can show you. Thank you.
Okay, seems there are no more questions, so we'll move on to the last talk. Do you have the...
Thank you, Dominique. So for our last presentation will be by Nick Ackerley on the field calibration of weak motion seismometers using strong motion accelerometers as reference.
Thank you, Benoit. My name is Nick Ackerley. I work at the Canadian National Data Centre. I'll be presenting some work I did with an undergrad student, Callum Irving. Our work is a little bit like Dominique's. It could be seen as proposing a different transfer standard, but in addition, we're proposing the possibility of calibrating the transfer standard in the field. In any case, we're working towards using these techniques for absolute calibration of the Canadian National Seismograph Network. My knowledge of the current state of the art of absolute seismometer calibration is actually from previous CTBTO S&T conferences. As I understand it, the main struggles in the lab are at the very edges of the passband, and I personally have been taking special interest in the temperature sensitivity of sensors. In fact, there's a very interesting paper on this topic on Thursday from the group at Sandia, Doug Bloomquist, and I think the question of temperature deserves more attention, because once that lab-calibrated sensor is deployed in the field for a side-by-side test, the temperature is likely to be different. I'm also wondering about the possibilities of the sensor being damaged in transport. Also, the lab calibration method seems extremely equipment and labor intensive. So I'm going to take a little detour on theory to start. Control systems theory. On the left, there's a very simplified diagram of a feedback control system. The basic idea is that there's a forward path labeled A and a feedback path labeled B. Excuse me. Yeah, on the left. So there's the forward path A and a feedback path B. And a basic property of these systems is that for sufficiently high loop gain, the A times B or beta, the response of the system is determined by the feedback path alone. In a force feedback inertial sensor, an electrical calibration should not change the loop gain, may introduce a low-pass filter, and crucially, it injects current into the force transducer. And that, on the right-hand diagram, the details of the diagram aren't important, but you can see the IC, a calibration current being injected into the force feedback transducer. And if you follow that current around to what was the input, the ground motion input, and then out to the digitizer, you realize that suddenly the force feedback transducer is part of the forward path. It's not part of the feedback anymore, so it doesn't determine the response. So the other thing I should note here is that those force feedback transducers are typically magnets with coils wound around them, and the magnet strength and the coil resistance can both be temperature dependent. So for me, knowing this, I'm proposing to only try to do absolute calibration at mid-band in the field, and really focus on this one otherwise unmeasurable by electrical calibration parameter, the force feedback transducer. So the method consists of 4 steps. First, we do an absolute calibration in the field of an accelegraph using gravity. This actually just takes a few minutes. Second, we immediately do a side-by-side calibration with a weak motion seismometer. This can take a few hours or many hours depending on the ambient noise and the desired accuracy. Third, we do an electrical calibration of the accelerometer and seismometer. And fourth is we combine all the results and add up the sources of errors. So most of the slides that follow focus on those first 2 steps. Absolute accelerometer calibration works by taking readings right side up, whoops, and upside down and taking the difference. The main requirement is a 6-sided box jig, which facilitates accurate placement. It's shown in the picture on the right in an upside down position. The even trickier position is the one where the cables are pointing down and you have to stand it upright without interfering with those cables. The instrument has to have a clip level of at least 2 Gs, and we place the sensor on all 6 sides to get 3 sensitivities. The picture shows a leveling plate, which is not required if you have a flat, level surface. And the whole process takes a few seconds per side and a minute total. So we did that for a bunch of, over a couple of days in spring in Canada, where the temperature varied by 20 degrees or 30 degrees. And the accelerometer itself has, not surprisingly, a fairly strong temperature sensitivity. Furthermore, while the instrument is heating or cooling, the errors are larger, so that tells us that it's important to let the temperature stabilize before doing this test. To convert the readings to a sensitivity, you need an estimate of the local gravity in meters per second squared. We found a model called GGM+. It stands for Global Gravity Model Plus. It accounts for both the ellipsoidal shape of the Earth and topography. It uses GRACE satellite gravimetry data and shuttle radar topography mission topography. On the right actually is a simple histogram of that data. You can see that it varies by about 0.15% to minus 0.35% relative to the standard value of G. If we didn't account for this, it would bias our calibration. This model is huge though, like 27 gigabytes. So we resampled it at a coarser grid, and we checked what the error was after our resampling, and it's quite small, many 0.05 of a percent. So we've developed a tool that facilitates this calibration process and uses the regridded gravity data and produces a station XML file. The whole process takes under 2 minutes. Is this working? Can you advance it? It's not working for me. Thank you. So next we do our side-by-side tests. We monitor the temperature of the sensors throughout the test and keep the data at the end where the temperature is stable to within some tolerance. This shouldn't matter for a sensor that is already in the field, but it will matter for the reference sensor, especially if you just pulled it out of the trunk. At this point, there are many ways to process the data. What we do is remove the response and bandpass and do a linearly squares on the 3-component time series. Can you advance, please? The first consideration in side-by-side testing is what's the signal-to-noise ratio, or SNR. The 2 graphs in this slide came out of an earlier work term with Callum, where we surveyed the Canadian National Seismograph Network and Earthquake Early Warning Network for misalignment and timing errors. Both of these plots have as the x-axis the duration times the SNR. On the left is the relative timing error expected, and on the right, the relative misalignment. What we did was take a high-fidelity broadband signal and degrade them with random amounts of white noise and analyze signals of random duration. So on the right, you can, for any desired level of accuracy, you can pick off the required duration times peak SNR to get the estimated 95th percentile error. So for example, to obtain a 0.1% error, you need 9 hours at 25 dB or 2 hours of 37 dB signal-to-noise ratio. Can you advance, please? So you can do a shorter test with low-noise sensors. On the right is a typical probabilistic power spectral density plot for a Titan accelerometer in 2G mode. And we have about 25 dB of SNR, which means we'll take 8 or 9 hours to get 0.1% accuracy. But the Titan has a nice feature. You can change its clip level, and if you reduce the clip level to quarter G, the noise floor is 12 dB lower, and the test need only be can be 4 times shorter. So to make sure that this is okay, we actually did some checks, did some calibrations of the accelerometer using different full-scale modes, and found that they agreed to within 0.01%. So we're confident that you can change the gain setting on the accelerometer in the middle of a test, or between tests, between step 1 and step 2. I'm going to quickly get through this. The electrical calibration, I'm glossing over it a little bit, but I will note that there's a slight difference in the response of an accelerometer between DC and 0.2 hertz, which needs to be accounted for. So the next sequence of slides has a look at, is an accounting of the errors. Oh, I'm sorry, can you advance? Thank you. That's the response. On the left is the Titan SMA, on the right is the Trillium seismometer. And advance again, please. So here's what our error budget looks like if we don't account for temperature and don't account for local gravity, just use the standard value for G. The total error RMS is almost 1%. So we do, advance please. If we first account for temperature, we're doing much better. The total RMS error is 0.2%. And advance, please. If we then account for the local value of gravity, the total RMS error is approximately 0.2%, which is looking pretty good. But the wild card here, advance please. The wild card here, oh, one more click. Oh darn, okay, sorry, back please. I'm just going to highlight the noise error entry on this slide at 0.06%. That's assuming a fairly high signal-to-noise ratio and a fairly long duration test. At the Canadian Hazards Information Service, the pressure is really on the field installation engineers, and if we're doing this opportunistically because, say, they're changing a cell modem at the site, they're not going to want to spend more than a few hours at the site. So this is the question: is what's the noise level, the ambient noise level at the particular site, and how long do we actually have to deploy a side-by-side test there? So that's really the controlling number in the error budget once we deal with temperature and local gravity. Advance, please. So in summary, field calibration of strong motion accelerometers can greatly simplify the field calibration of weak motion seismometers. I should note that it can't replace lab calibration, especially for verification that the calibration input and ground motion output responses are as the manufacturer specifies. Also, I want to note that as far as I can tell, neither GRACE nor the GGM Plus model have been calibrated in or verified in any traceable way. But still, I feel pretty strongly that gravity itself can serve as an important reference signal in the field for the calibration of weak motion seismometers. At the National Data Center, the next steps are training our field operations staff. That started, but we haven't actually started taking advantage of field maintenance to do opportunistic calibration of CNSN stations. We do hope to, and I personally am looking for opportunities to compare our calibration results and method to laboratory calibrations that some of you may be involved in. So thank you for your time.
Okay, we have time for a few questions, so does anyone have anything to ask Nick?
So if you had accelerometers at each of the sites as well as the broadband high gain system, and you compared your carry it around accelerometer with the accelerometer, would you need to use as long of a time series in order to make sure that the local accelerometer was calibrated correctly, and then you could use the local accelerometer, which is sitting there all the time at the same temperature as the broadband, and do the calibration for the broadband?
That's an excellent question. It very much depends what the noise floor is of the instrument, the accelerometer is that's already deployed. How good is the signal-to-noise ratio that you're getting at that site? If you're getting 20 or 30 dBs daily, then absolutely. If you aren't, then no, you need an accelerometer that can both see 2Gs and see a lower, at a lower clip level, give you a lower noise floor and more signal-to-noise ratio. But you're right, the test could be sped up by the introduction of an intermediate standard, and that intermediate standard could even be a weak motion sensor.
Thanks, Nick. That's really interesting approach to having some in situ traceability for an accelerometer. I'm just kind of noting your discussion about the main applicability for the mid-band frequencies. Curious if you have any thoughts on approaches that could be extended to extend a traceability on an accelerometer more broadband, especially be able to look at the corner frequencies where strange things happen.
The method as proposed, no. I'm really relying on ambient noise, and that's what locks me into mid-band. I just don't think there's, you could generate higher seismic noise with some sort of thumper device at the site, but I worry about its propagation and whether it's near field, far field, is it a plane wave? I feel like that introduces all sorts of problems. And the reason I'm focusing on mid-band is because if you can pin down the absolute sensitivity of the sensor at just one frequency, anywhere at all, then you're solving this problem of the part of the instrument response that's unreachable through electrical calibration. I personally think electrical calibration is the way to monitor high frequency and low frequency, the two corners, all the way up to Nyquist in the field. It's easy to do. You can do it many times. It's cheap. That's the way to cover the full frequency band. So then you just need to pin the response at one frequency somewhere in the middle. And guess what? The microseismic peak gives us signal to noise in such a way that we can do that.
Thank you.
There's another question from...
Okay, I have a question too. Maybe before you make the calibration, maybe you have a geological study to try to determine the slides of the ground or something like that to make the calibration on the field when you try to do for the accelerometer sensor?
Are you talking about the absolute calibration of the accelerometer or the side-by-side calibration?
Okay, thanks. It's for the accelerometer calibration.
Yeah, I don't think it matters very much what the surface is. You can do it anywhere. We took care to make sure that the jig for calibrating the accelerometer was level, but it's relatively insensitive even to a few degrees of tilt. It's a 1 minus cos theta sort of thing, and it's not a very significant effect. So if there's some, say, localized tilt during the test, I don't even think it would be very sensitive to that.
Thank you. We have time for one more question. Thomas, please.
Yes, thank you. It was very, very interesting presentation. I'm just not sure whether I missed something or maybe I'm too picky as being a metrologist, but the method for the calibration of the accelerometer relies on the hypothesis that the temperature has no influence on the response function over frequency. So you're measuring or doing the transfer between the two sensors at a frequency, so not at DC, but your traceable calibration, traceable to G local calibration of the accelerometer is only at a DC kind of calibration. Or are you rotating it in gravity to get to the same frequency where you do the transfer?
I'm going to answer the temperature part. of your question at the beginning, if I understood correctly. I might have to get you to ask again, but in principle anyway, all the steps can be done at the same temperature. Interestingly, the accelerometer that you field calibrate doesn't even need to be at the same temperature as the sensor could be downhole, for example. It just needs to be at a stable sensor, a stable temperature, and at the place where you're doing the side-by-side calibration, so that you're capturing the mid-band sensitivity at the moment of the side-by-side test, the absolute mid-band sensitivity.
But your reference you're tracing to is a DC calibration at G local, right?
But you can do the calibration in the field. So you can do the electrical calibration at the operating, for the field sensor, it's operating at that temperature, and you can do the full frequency band calibration. And then for the accelerometer, you can do the calibration at that time as well. So I feel like it's all sorted out in the field, potentially. Thank you. It's a great question.
Okay, thank you very much, Nick. So that was the last of the presentations for this afternoon. So just remains for me to thank you all for attending, and special thanks to the presenters today for their talks. Yes. So it's not the end of the session. So we have two more things to tell you about. There is a poster session on Thursday afternoon with very many excellent poster contributions within this session topic. So please do try and check those out. And then tomorrow morning has been announced already. We have a metrology for the IMS operations side event. We'll be also in this room from 9 o'clock tomorrow morning. So if you're interested in this topic, please do try and come along to the side event tomorrow as well. And don't forget the posters on Thursday. Okay, thank you very much.
And don't forget to vote, yes, in the app.
They need these lights, they're quite off-putting.
I think you get used to it.